All right, so trigonometric equations. First thing to recognize is trig equations. Trig equations are, a lot of times they're called transcendental equations because they're non-polynomial. Okay? So we got polynomial equations. Now we all know what a polynomial equation looks like. It's the a to the n x sub n times a to the n minus 1 times x to the n minus 1, all the way down to a sub 1 x to the first plus a sub 0, right? Anything of that form is polynomial. Trigonometric functions, logarithmic functions, things that are not that, a lot of times are referred to as transcendental, okay? So that's kind of what we're doing here, but a trigonometric equation is obviously anything that's going to have a trig function in it. So anytime you see sine, cosine, secant, cosecant, tangent, cotangent, any of those things, you see them in an equation, you got a trigonometric equation. There are going to be times that we have to recognize and apply appropriate identities to start working with the trig equation. I'm going to try to show you some categories, try to show you kind of how every one of our trig equations is going to kind of filter down into maybe 4 or 5 different approaches, okay? But you might not be able to recognize one of those 4 or 5 approaches until you make a substitution, okay? Initially, an equation might seem really challenging and almost impossible, but once I make a substitution, it starts to clean things up a little bit, and then the category that it belongs to kind of surfaces, and then you say, okay, well, I know that approach, and I can solve that equation that way. So that's kind of the plan over the next couple. I think I want to spend, I don't want to say the entire next week over this stuff, but the rest of this week, maybe Monday, Tuesday, maybe even Wednesday of next week, working with solving trigonometric equations. Okay, I just find that they're very important to us. There's a lot of real-world applications for trig equations. Okay, now a lot of obviously we have technology that actually incorporates this stuff into it and solves this information for us and gives us this information back. If you've ever looked at an EKG or anything like that, an echocardiogram, okay, for your heart, right? Okay, or anybody got an Apple Watch and it shows the electromagnetic pulses or whatever of your heart and all that kind of stuff. So those are sine and cosine waves, right? Okay. Now they're being adjusted, they're being multiplied together, that kind of thing. But that's how we interpret them. If you've ever looked at, you guys know what an oscilloscope is? What's an oscilloscope? All right. So if you've ever like recorded sound, okay, you guys you play like you guys you have like a media player on your computer or your phone, and when the sound is being played, you can see like bars going up and down. Okay, so that's kind of like an oscilloscope. Basically, it shows the sine and cosine waves of a noise, okay, of sound. Within those things, there's going to be the need for data to be interpreted and provided for the user. These trig equations are kind of inside the programming of that stuff to provide that information to you. Okay. All right. So we're going to be interested in solving things that look like this. Now, this first one here, obviously a trigonometric equation. Okay. But it's a special kind, right? That's your identity. Okay. And the identities then are things that we're going to make substitutions with. The other two, those are more along the lines of what we're going to start off with on the onset, okay? But if you think about these, all they are, my tablet go. All these things are, my voice, I don't know what's happening here. My voice, if it's finally hitting puberty or allergies or something like that. Probably not puberty. Huh? Yeah, maybe I'm pregnant. I don't know. So does this look? So sine theta is our unknown, right? Okay. So does that look like 2x minus 1 equals 0 if I write it as an unknown? Okay. Can you solve that equation? The way you solve that equation, exactly the same way you solve that one. Okay. And if we can make that connection throughout all the things that we do here, you should be able to rely heavily on your algebra skills. And that's kind of why college algebra comes before trigonometry. I want to investigate kind of it ends up being the last step of every single equation you deal with trigonometrically. Okay? So this thing here is going to be what is generated in your last step of every trig equation. Now, it might be cosine, it might be secant, cotangent, tangent, whatever. And it might be 1/2, but it might be some other number. Okay? It could be any number that we arrive at. Okay? So I want to show the technique here. And this is kind of analogous to what you did in Algebra 1. If you think about the first kind of equations you solved in Algebra 1, or maybe even the 7th, 8th grade, you did things like this. You had 2x is equal to 1, right? Or you did 1/2 x equals 2. Those are the types of equations you started with because they're the last step of every equation, right? So then you divide both sides by 2 and got x equals 1/2. Or here you multiply both sides by 2 and got x equals 4, right? And that's great, that's awesome. But the next thing that you did, you learned how to do those. You learned the process for isolating the variable that way. We then added something here. Or here, does that make sense? And now we added one more operation. So, okay, now we're going to subtract 3 and then divide. Okay, or subtract 3 and then multiply by 2. And then what do we do? Well, we built upon that and we said, well, let's look at the distributive property. And let's look at how that changes things. Okay, does that kind of make sense on that? So that's kind of how I want to address these trig equations. Okay, we're gonna start with ultimately the last step. Okay, sine of theta is equal to 1/2, and then we'll say, okay, well that probably came from 2 sine of theta equals 1. Does that make sense? So this came from that. But I want to start with this last one. Give myself a little bit more room here. Oh my God. All right. So what we're going to do is that you've got choices here. But my hope is that we understand this stuff well enough that we realize these two choices are really the same thing. I can either use the unit circle. Okay, know the unit circle, what it looks like, and say, okay, where is the y value 1/2? And then work my way back inside to the angle that provided that, right? Or I can actually use the algebra that actually allows that theta to be pulled out of this equation. Because we know that when sine inverse of sine theta, for any theta, these two things are going to do what to one another? Cancel out, right? And leave me then, theta is equal to sine of 1/2. Sine inverse of 1/2, sorry. And then grab my calculator, right? Why don't you grab your calculators real quick? The last class we were talking about this, and the idea here, guys, is if you're in radians, so they're going to ask you two types of questions. They're going to ask you to find solutions in radians, and the next question might say find the solutions in degrees. Next one might be degrees, next one might be radians, next one might be radians, next one might be degrees, and they flip-flop back and forth. Okay? If this question was in radians, okay, they're going to want pi over 6 as an answer, right? Does that make sense? If I type in sine inverse of 1/2 on my calculator, I'm in radians, it's going to give back, I think it's like 0.52 something. Okay, 359. If I look at that, do any of us know that that's 5 or 6, like right off the bat? No. Okay? However, even if the question asks us to write our units in radians, if I did things on my calculator in degrees, when I do degrees here, I can go sine inverse of 1/2. What's that going to spit back to me? 30 degrees. Now do you know if that's pi over 6? Okay, so that might be an option. Do everything in degrees, and then convert that to radians when they want radians. Okay, especially if you're going to rely heavily on your calculator. Okay, my hopes are we rely heavily on our unit circle and not so much our calculator, but obviously it's up to you. All right, so when we look at the sine inverse, and this is kind of understanding what the sine inverse does for us. Remember, sine inverse looks like this thing right here, right? Okay, I think. Yeah. Is that the right one, or does it go that way? Or it's this way. Yeah, it's this way. It's that one. But that gives me results between negative pi over 2 and pi over 2. Does that make sense? So if I make that look like a unit circle, my sine inverse is only going to produce things between negative 90 degrees and positive 90 degrees. A lot of times they're going to ask you to answer things between 0 and 360. Okay? So let's say that we get 30 degrees here. Okay, that is the answer, so it'll be about right there, right? And that ordered pair will be radical 3 over 2, comma 1/2, right? And that's at 30 degrees there. Is there anywhere else on the unit circle that I get a y value back of 1/2? Yeah, 150. So I have an alternative solution over here with that ordered pair, negative radical 3 over 2, comma 1/2. And this angle here, that blue angle is the same as this 30-degree angle, right? Okay. However, we're interested in knowing that angle right there. So that would be 180 minus 30, right? So our other option for theta is 150. That solution, 100% of the time, is never provided by your calculator, because sine inverse is only going to give you between negative 90 and 90, right? 150 is not in that interval. Okay? But 150 does satisfy this equation. Type in, make sure your calculator is in degrees, type in sine of 150, and you get back 0.5. Okay? Type in sine of 30, you get back 0.5. Okay? I think that escapes people sometimes. Try to realize and remember that these are equations, so when you get solutions, plug them back in, see if they work. Okay? Now, here's the thing that I think people struggle with is, if I have a quadratic equation, I know I have either 0, 1, or 2 solutions, right? If I have a cubic equation, I know I have 0, 1, 2, or 3 solutions, okay? So we know from our other types of equations kind of defined amount of solutions we're going to have. Sine, cosine, tangent, it's maybe not so easy, okay? And it depends. Usually the sine is going to give you 2, cosine is going to give you 2. Tangent will give you 2, but there's a question here in a little bit that we see that we work with the tangent, we get 4. Okay? So there's the argument that, yes, plugging these back in tells me that these were correct, but maybe it doesn't necessarily, if I don't understand what's going on, it doesn't necessarily tell me that they're all of my possible solutions. Does that make sense? All right, so let's kind of talk about what we're doing here with GeoGebra. When we look at, and I'll post this, I don't know, I've been having trouble with using GeoGebra's, like sharing, like you post this to their website and then you copy the HTML to embed it in your Power or your website. And it's been messed up lately, so I don't know when I'll get this to you, but I'll get it to you at some point. All right, so what I'm looking at here, this is the unit circle that we developed at the beginning of Chapter 6. If you click on the ordered pairs, it puts them there. Now, to make it a little bit better when you're looking at this on your own, you might want to go to labeling or font size and chop that down a little bit. But just for our purposes, so we can see things a little bit better, make that a little bit bigger, and I'll hide them. Okay? But what we're doing when we say sine of theta, our calculator, when we said 30 degrees, right? or 1/2 was the y value. So I find the y value of 1/2, and it gives me this 30 degrees, correct? Okay. Now, because the unit circle is symmetric about the y-axis, that is where this ray here is coming into play, because that angle right there is 30 degrees, and so is this one, right? So this is the alternative solution that we get when sine of theta is equal to 30. Or sorry, when theta is equal to 30. When we find theta to be maybe 45, there would be the other solution that it gives us, right? So we're kind of using, this applet here shows us that additional solution that we need that our calculator doesn't provide us, right? Okay? Because our calculator is just going to give us, for the sine, just the stuff in that interval there. Okay? There are, I think my TID9 will actually give me, we're going to come up with infinite solutions here in a moment. I think my TID9 will actually write those out for me in an equation, which is nice. So there is technology out there that will kind of address this concept for you. If I deal with cosine there now is going to only give you solutions between 0 and 180, the cosine inverse. Okay, so it's only going to give you stuff in the first and second quadrant. So this is showing me then, if I find a first quadrant of cosine that was 30, the theta was 30, then I'd also have to show 330 would work too. Does that make sense? Okay. And you can change it, you can move that around, and it always pairs up those two angles that you need for cosine. Okay. I don't have tangent in here yet. I don't know if I'll put tangent in there. Just get tangent's a little bit more involved. Okay. So those are our two solutions, 30 and 150. Does that make sense to everybody? Okay. I want to look at this graphically. I want to look at it. So we looked at unit circle-wise. Let's look at it this way. Right now, I've got, let me just hide some stuff here real quick. Show object, you see that. Okay. So I typed in my equation. Sine x as one function, y equals 1/2 as the other function, right? Graphically, we know the solutions to those, or to that equation, that sine x equals 1/2, is where these two things cross, right? And it's the x value of where they cross, right? They're always going to cross at the 1/2, right? The y value there. But the x values are different, okay? You told me, we worked through this and found x to be 30 degrees, right? Now, I did everything here, and GeoGebra is set up to work with radians. Okay, so I went ahead and just rewrote my x-axis as radians. So if I said 30 degrees, we were actually looking at x equals pi over 6, right? Does that prove to you why that was a solution there? That demarks the location and where those two curves, the red one or the orange one and the green one, intersect. Okay? What about 5 pi or 6? Okay, those are my two solutions, right? Now here's the thing. Those are the only two solutions that came from the unit circle, because the unit circle only shows things between 0 and 2 pi, right? The unit circle is only working inside that there. Okay? But what if I want this solution out here? Because that is a solution as well, right? That's where those two things cross. How can I find that solution? Say it again? Let me do that. Let's take this. Let's take this point right here. So let's do my intersection here. Oops. I want to do the intersection of that and that. It might take some time. Gavin, you okay? long night. Okay.
Outside of the blue area?
There we go. So at that point, and let's see here, this point here. Come on, there we go. All right. So E and F. Those 2 points, would you agree? So it did give me some other points over there. Would you agree that E and F are on the same horizontal line? Okay, so if I took the x value of F and subtracted from it the x value of E, it gives you 6.28, right? What's 6.28 the same as? 2 pi. Okay, so this was that extra solution out here that modeled or resembled this one, right? A is the next point out here that models that one, right? Okay, so let's look at, we can do x of A. If I do minus x of F, it's going to give me 2 pi. If I go x of A minus x of E, does anybody know what that's going to give me? E was that first point over there. What's 12.57? Any guesses? It's 2 pi times 2, or plus 2 pi, right? It's 4 pi. Okay? So, what we're seeing, hopefully you recognize this, is that if I want extra solutions that are outside 0 to 2 pi, if I want those solutions that are outside there, what do I need to take to E? What I need to do E's x coordinate to get F's x coordinate? Add 2 pi. Okay? So, when we looked at our solutions here, and we found out that theta was pi over 6. Okay? Theta was also, from the unit circle, 5 pi over 6. But those are only 2 solutions between 0 and 2 pi. A lot of times we're interested in infinite solutions. So to find another solution, I add 2 pi. Add 2 pi. Does that make sense? And that's going to give me a total of 1 solution, 2 solutions, 3 solutions, 4 solutions. Does that make sense? Can I find more by adding another 2 pi? And add another 2 pi, right? Can I keep playing this game and adding 2 pi as many times as I want? Right? Maybe let's say I do that an infinite number of times. That would be a pain in the butt to write, correct? All my infinite solutions. So what we do when we write infinite solutions is we write an equation that produces them. Okay? And basically what I'm doing is I'm adding just multiples of 2 pi, right? Well, adding multiples of 2 pi, if I go 2 pi plus 2 pi plus 2 pi, is that 2 pi times 3? Is this 2 pi times 4? 2 pi times 5? Well, what if I don't know how many I've got in there? What if it's something like that? It's 2 pi times some value of k, where k is actually the number of objects that I have there, right? Okay. Now, the number of objects that I have there, are they always whole objects? Do I ever have half a pi in that? Or a third of pi or anything like that? So k is an element of your integers. Meaning that if I want to find that first one, k would be 1. So adding 1 to it, or adding k, or making k 1 would be pi over 6 plus 2 pi. If I want to find that point A that was out there that had 4 pi attached to it, it would be pi over 6 plus 2 pi times 2. K would be 2. And that would add on 4 pi, right? If I want to find another one outside there, let's make k 3, and then I would add on 6 pi to this. 4, I'd add on 8 pi, 5, I'd add on 10 pi. Does that kind of make sense to everybody? Okay? So it's finding all those extra solutions that model the original solution pi over 6, but on the outskirts of that original region 0 to 2 pi. Now, if k is an integer, it could be negative, right? So it's going to actually find the solutions that are to the left of the y-axis as well, which is nice. Okay. Down here, I would do the same thing. 2 pi k. K is an integer. Okay? You're going to be asked to write your answers like that in your homework sometimes. Okay? I don't think that you have. I think they already have it typed in that k is an integer. You don't have to type that in. I'm just going to ask for 5 pi or 6 plus 2 pi k. Okay, so that's nice. And that makes sense because what is the period of sine? It's 2 pi, right? Okay, so the sine period is 2 pi. What's the cosine period? Same thing, right? 2 pi. What's the secant period? They're 2 pi, right? What's the cosecant period? 2 pi. What's the tangent period? Pi. Okay? So what I need you guys to understand is that when we go sine, cosine, secant, cosecant, all of those are going to be kind of, they want the infinite solutions. You're going to write your solution of theta, whatever that is, and then you're going to add to it 2 pi k, where k is an integer. It's systematic. It's the same thing over and over and over again every time you see those. Okay? But I want you to realize the reason for that. When I was in school, they just said, well, add 2 pi to that, or add 2 pi k to that, and you're good to go. Okay? And I think it makes more sense if we understand why we do that, instead of having you to kind of dive into that on your own and try to figure that out on your own. Tangent and cotangent, they are different. Tangent theta, cotangent theta, okay? When you find those, you're going to go theta plus pi k, where k is still an integer, okay? So those things, those need to kind of be embedded in your mind when you're doing these. What is problematic, what happens all the time, and I'll even make this mistake, because there's 4 of the ones that have 2 pi k, and there's only 2 that have pi k. You can see that the red ones, we would deal with more of those just because of the nature of having more of them, right? So you're going to have more equations that deal with sine, cosine, secant, and cosecant. And you get trained because I see a sine, I see a cosine, I see a secant, I see a cosecant, I see a cosecant, I see a sine, I see a cosine. And I'm always going 2 pi k, 2 pi k, 2 pi k, 2 pi k on the end of my answers. And then the next question they give you is a tangent, and what have you trained yourself to type in? 2 pi k. And that's why people miss those questions. So just be careful that we're always thinking when we see a tangent and cotangent that it's a little bit different because the period is different for those functions. Okay, so let's go through and actually do a couple like full-on questions with this, and they're not that terrible of questions today. All right, so we're going to. You can do this one of 2 ways, guys, and I kind of ran out of time showing the last class this. You can recognize that is your variable term, right? And you can just work with the equation, leaving that in there and say, okay, well, I'm going to isolate the 2 cosine theta, make it 1 equal 1, and we'll divide both sides by 2 and get cosine theta is equal to 1/2, right? Okay? Or, if you want to do this, we did this in algebra or college algebra, let's write that u is equal to cosine theta. And I think this is going to benefit some of us. Because now can I write that as 2u minus 1 equals 0? And now it's strictly algebra, right? 2u is 1, u is 1/2. But what was u? Cosine theta. Okay? That's a procedure that I think might benefit some of us. It is a procedure that there are times we have to use that. Okay? I think with these kind of smaller, simpler questions, you don't necessarily need to do that, but it's an option. Okay? And I think it's a really good option. I think that u substitution is an underused process in mathematics. Okay? I think it's very, very beneficial. Okay. So now we're looking at this thing and say, okay, when is cosine theta equal to 1/2? So again, using your unit circle or using your calculator, you're going to essentially think about, okay, if I'm traveling around this thing right here, where is the x value 1/2? So I'm looking at this thing here. When do I come to an x value of 1/2? It should be right there at 60 degrees, right? Okay. So our calculator, it will give you that 60 degrees. Okay. If you type in cosine inverse of 1/2, make sure you're in degree mode, it will give you 60 degrees. 60 degrees. Okay. If we look at this, okay, the x value up here is 1/2, y value is √302. But isn't the x value down here also 1/2? Okay. So what would that angle right there be? It'd be 60 degrees, but it's going in the negative direction, right? So we'd label it as negative 60 degrees. Okay. Now, we don't like to write negative 60 degrees, okay, as our solutions. So if negative 60 shows up, so theta is also equal to negative 60, what should I do to that to make it positive? Add 360 to it, and now I get 300 degrees. That's usually the one they're asking for. Okay, and they'll ask that by doing it this way. They'll say, here's an equation, find the solution between 0 and 360. Well, when I find negative 60, is that outside that interval? So they're saying that's not going to work. You know, we don't want that one. We want one that's in this interval. So you got to convert it over. Okay. If they don't write that, then I guess negative 60 would probably be an okay answer. Does that make sense? It's all predicated off of how they're asking you in the directions to leave your solutions. Let's write so 60 degrees or 300 degrees. Okay. That would be in degrees. We can also do it in radians. What would be 60 degrees in radians? pi/3. And then 300, hopefully we know what that is using reference angles. It'd be 5 pi/3. Okay? If I'm looking at this one here, and I want infinite solutions, I'm going to add, let's actually do these bottom ones, because this is what we talked about. We do 2 pi k, right? 2 pi k, 2 pi k. Up here, what am I going to add? 360k. Okay, so just know kind of the difference there. Or if we're in radians, obviously, a cycle around the unit circle is 2 pi. In degrees, it's 360. Okay. Therefore, if I'm working with tangent or cotangent, it'd be, in degrees, it'd be 180k, right? That's what pi is. So just be careful with that. I get a lot of people come, I've been doing this question, I know I'm doing it right, I'm writing everything the way I'm supposed to, and I look at their answers and they got 60 plus 2 pi k. Where, I mean, if they convert the 2 pi to 360, they're right. So it's just a typo type thing. Now, let's say that somebody wrote theta here as negative 60 plus 360k. Is there anything wrong with that answer? Think about k being 1 here. If k is 1 here, you get 660, right? Doesn't k have to be 2 there to get that 660? Does that make sense? But do they both, at some stage, provide 660? Yeah. If this one was 0, okay, that gives me 300, right? Doesn't this one have to be at 1 to give me 300? But they both provide 300, correct? So there are various ways, if they're interested in asking the infinite solutions, there are various formats of writing that. Okay? As long as your format produces all the same solutions as your neighbors, then you're both right. My hope is that we write the blue one, start off with the smallest positive angle first, and then add your 2 pi k or 360k. But if you wrote this one, there's nothing wrong with it. Okay? But if they ask for the finite solution, okay, go back to this. If they ask me for finite solutions, and I gave back maybe negative 30 degrees, or actually it would be negative 150. If I gave back that, That's not going to be inside that blue range, right? So that would be a problem. So when they want infinite, this blue range will not be there. They want finite, this blue interval is what we're looking at, because there's a finite number of solutions inside there, right? Okay. So let's do the next one. Tangent and cotangent, they're a little tricky sometimes. Obviously, if this was like x squared minus 3 equals 0, or u squared minus 3 equals 0, you could solve this a couple different ways. You could use the square root method, right? U squared is equal to 3. U would equal plus or minus root 3, right? But should we have defined u as? There's tangent, right? Okay. So tangent theta, as we work through solving that one right there, we're going to isolate tangent, and we're going to get it to equal plus or minus root 3. Number one mistake people do is that. They forget the plus or minus, and that misses half the question for them. Okay? So we need plus or minus here. It is a big deal. So really what's going on here is that we're asking two questions. When is tangent of theta equal to positive root 3? And when is tangent of theta equal to negative root 3? And I like to separate them like that because it reminds me of what I've done and what I need to do in my work. If we were in degrees, these are the two degrees that radical 3 shows up with in the unit circle. This one, if you remember, though, is radical 3 over 3, and this one is radical 3. Okay? So we're picking off, so the question is, what angle of theta will give you radical 3 back? It's 60 degrees, right? So theta is 60 degrees. Okay? If you were to type on your calculator, and this is why I like using my calculator in degree mode. If I was in degree, if even the question asked, write your answer in radians, I would still do things in degrees. So I could go tangent inverse of root 3, and so spit back 60, right? And then I can convert that 60 to pi over 3 if that was the desired unit left over. Let's think about what the calculator is doing for us for tangent, though. It is only ever going to give you things in those two quadrants. It's the same interval as the sine inverse. So tangent inverse is the same interval as the sine inverse. So negative 90 to positive 90. And we looked at root 3. Okay, so we're looking at that angle right there. That was 60 degrees, correct? It was tangent was positive root 3. Are there other quadrants in which tangent is positive? What other quadrant is tangent positive? Third quadrant. So there's a solution that's down here that we got to figure out. Okay? Now there's two ways of doing this. And they're really the same thing, but two ways of maybe visualizing it. The sine function is, there's that x-axis symmetry that's going to allow us to find the two solutions. The cosine is there's a y-axis symmetry that's going to allow us to find the two solutions. The tangent function, because it's sine over cosine, is actually an odd function, meaning it has symmetry across the origin. Meaning, back to college algebra, if we reflect across the x-axis and then reflect across the y-axis and then reflect across the x-axis, it should give us the angle that we need. Okay? So if I do that, how big? So when I reflect, reflections are isometries, meaning distance is saved or preserved, meaning that angle there and that angle right there have to be the same, right? So that angle right there is 60 degrees. When I reflect that over the x-axis, that angle there is 60 degrees. Does that make sense to everybody? Okay. When I want to find out what theta is, remember, theta is always an angle from standard position. It's always that blue angle. So how do I find that? 180 plus 60. Okay, we know that is 180, right? And all we're doing then is, through that reflection, is we're attaching another 60 degrees. So 240 would be that additional solution. Okay? Now, my picture kind of stinks here, but let me do this. If there's some metric about the x-axis and the y-axis, kind of back to back. That is the same thing as a 180-degree rotation. So I think maybe sometimes what a quicker approach is to realize that if I use my x-axis here, and I use that terminating ray and extend that terminating ray as a line, that angle right there and that angle right there, do you remember what they're called from algebra? Or sorry, from geometry? They're two angles in which are formed by intersecting lines. What those two angles are? I heard it. Somebody say vertical? They are vertical. Does anybody remember what the rule or relationship between vertical angles is? Huh? They're the same. They're congruent. Okay. So if this one was 60, what's that one? 60. And that, I think, allows me, it's a little bit quicker because now I bypass having to look at that reflection there and look at that 60. Either way is fine, and in either way is really the same thing. But I'll use the vertical angle aspect of things to find those. Okay. Now let's talk about tangent of theta over here. When is tangent theta equal to negative root 3? Okay. Well, if you type that in on your calculator, negative root 3, tangent inverse of negative root 3, what's it give you back? What'd you say? Yeah, it's going to give me back this angle here, which that angle there is negative 60. Does that make sense? That's what your calculator will spit back. But if it's negative 60, do I ever want to use negative 60? So what's the same thing as negative 60, though? 300. Okay. So if that's negative 60, if I extend there, isn't this angle here going to be 60? Okay. So then, again, theta is always from standard position, so it'd be to there. How big would that be? It'd be 120, right? Okay, it'd be the 180 minus. So this would get me all the way to 180. If I backtrack 60 degrees, it gets me there, so it'd be 120. Okay? So what we can do then, something that I think is useful, is to grab something like Desmos or TI-83, 84, whatever. Make sure you're in degree mode. If I type in, what was the equation? Tangent squared theta minus 3. And I should get 0 back, right? So I'll type in my answers that I found. We found one answer to be 60. Okay, now here's the thing. Doesn't give me necessarily the visual 0 back. But what is that number? That's 14 zeros followed by a 1, right? Is that 0 for our purposes? Yeah. So 60, what did we say that other one was? 300? Okay. 120. And then 240. Okay. If we're in or GeoGebra, if I type in tangent squared of 60, which is pi over 3, minus 3, there you see that one gives me 0. GeoGebra gives me 0. I don't know why it does, but some calculators do that. Some calculators, I don't know what they're doing. It's got to do with the fact that your calculator is not programmed with these. Your calculator, the sine function, cosine function, is programmed with what we call a Taylor series. Maybe I'll show. I don't know if I've shown that to you. Maybe I'll do that tomorrow and kind of explain why that's happening. But it's because the function that your program is using to approximate sine and cosine, we kind of blow it up there. We mess it up.